So, we begin our discussion on the analog subsystems. The first subsystem that we are going to take up is the resistors. So, as you know from your basic knowledge of circuits that resistor is a linear circuit element across which a voltage drop occurs when a current flows through it. So, if you consider a resistor connected between two nodes A and B, where the potential at node A is VA and potential at node B is VB, if VA is greater than VB, then current flows from A to B. Now, we know as per Ohm's law, temperatures and other physical conditions remaining the same, the current flowing through this resistor is directly proportional to the potential difference between its ends, and the constant of proportionality is the inverse of resistance. So, the equation basically comes out to be I equals to 1 by R into VA minus VB, where R equals to R is the resistance of the resistor. Now, if we talk of discrete circuits, then this R can be implemented in several ways. We can have a conventional carbon resistor, but in case of integrated circuits, we cannot have discrete components being added to the integrated circuit, and therefore, this resistance should be a part of the IC chip itself, because in most cases we want a monolithic integrated circuit. So, this resistance itself becomes a part of the integrated circuit. So, now this resistance is there are various ways by which we obtain this resistance. You can have a polysilicon resistance or polysilicon resistor. You can have N-well resistor. You can have bulk silicon resistor. So, there are n number of options by which we can realize passive resistance on silicon wafer. We can have a doped silicon wafer, where the doping where a part is densely doped with donor impurities, and depending upon the doping density, the resistance is going to vary. That means, as you go on increasing the doping density, there are more and more abundance of electrons in this part of the semiconductor wafer, and therefore, the resistance will come down. The other way is you can use a polysilicon resistor, where the resistance is much less, and typically for moderate range resistors we use a polysilicon resistor, but for all these resistors what we really end up with is a fairly large area of the IC is actually consumed with these resistors. So, in practical cases we seldom use these passive resistances, we basically use MOS resistances. Just for the sake of knowing, we will tell you, for all these resistances we typically specify the resistivity per square, resistance per square, or which is called the sheet resistance of the material, and you specify the area of your resistor as an integral number of the squares. Each square has got an unit dimension, and the dimension of your resistance is specified by the integral number of this unit square, which gives us the amount of resistance we are going to implement in the circuit. Now, let us see how to implement a resistor using a MOS circuit. Suppose I connect a MOS transistor in saturation by shorting the drain and the gate. It is why it is in saturation, because let this is the drain, this is the gate, this is the source. So, we have VDS equal to VGS, since we are shorting the drain and the gate, which implies VDS is greater than VGS minus VT, and this means this transistor is operating in the saturation region, and since this transistor is operating in the saturation region, therefore, the drain current for this circuit is given by ID equals to mu n CoX W by L, W by 2L, VGS minus VT whole square into 1 plus lambda VDS. So, you could recall the equation of the drain current of a MOS transistor operating in saturation. So, we are basically given by this kind of relationship to be this kind of relationship between the drain current and the drain source voltage. So, now if we find out del ID del VDS, then it is equal to lambda mu n CoX W by 2L VGS minus VT whole square, but this quantity is very small, since lambda is having a value of 0.04 per volt for an NMOS transistor and 0.05 per volt for a PMOS transistor. Therefore, this term has got a insignificant magnitude, and therefore, we can approximately keep this equal to lambda ID. So, this is basically the output conductance for the MOS transistor, and if we take the inverse of it, that is del VDS del ID, then this is equal to 1 upon lambda ID, which is basically the dynamic resistance of the MOS circuit. Now, if you see the VDS versus ID characteristics, you will basically get characteristics like this, and since this characteristics is somewhat similar to that of a p-n junction diode, so it is popularly known as diode MOS characteristics. Now, if you consider a MOS circuit like this, then you can write ID equals to mu n COX. If this transistor is operating in the active region, you can write ID equal to mu n COX W by L VGS minus VT into VDS minus VDS square by 2. Now, if we do del ID del VDS, then this is equal to mu n COX W by L into VGS minus VT minus VDS. So, if we do, so if we invert it, we will get del VDS del ID, that gives us L by mu n COX W into VGS minus VT minus VDS. So, now this from this equation we get the minimum voltage needed to turn on this resistance. So, if VDS equal to 0, then we have del VDS del ID equal to L by mu n COX W into VGS minus VT. Right. So, this gives us the on resistance of the transistor. So, this gives this expression gives us the on resistance of the MOS transistor. Now, if you look at the characteristics of this resistance, then this is R on and this is VDS. For an NMOS transistor, we see that when VDS equals to 0, it has got some non-zero finite value. Now, as you go on increasing VDS, the difference becomes lesser and lesser, and therefore, R on also increases, but notice that when VDS equals to VGS minus VT in that equation, that means when VDS equals to VGS minus VT, it becomes infinity, which means that VDS equals to VGS minus VT line is basically an asymptote to the curve. So, this is for an NMOS transistor. Similarly, for a PMOS transistor, the characteristics will be somewhat like this. So, if you consider the behavior of these resistances versus the normal ohmic resistor, these resistors are highly non-ohmic, and this is also mathematically evident from this equation, where you are getting a voltage to current relationship which is inversely proportional to the current flowing through the resistor, which is which is very much a departure from the Ohm's law. And therefore, these resistances are non-ohmic resistances, and therefore, since these resistances are non-ohmic resistances, we typically have to take care of the nonlinearity embodied in its behavior when we use it in specific circuits. And so, we see that both the NMOS and PMOS resistors are nonlinear. So, what if we have a parallel combination of an NMOS and a PMOS transistor as in a CMOS transmission gate? So the thing is that you need complementary clock signals to complementary pulses to turn on the NMOS and PMOS transistor, because we have to turn on both at the same time. The advantage is that the NMOS transistor will nicely pass the logic 0 and PMOS will nicely pass the logic 1, and therefore there won't be any threshold drop related problems as you pass the signal through this CMOS transmission gate. And therefore with this parallel combination you basically have a resistance characteristics like this, which is almost constant over a very large dynamic range of voltage, and therefore CMOS pass transistors are typically used in most circuits instead of only NMOS or PMOS resistors. CMOS pass transistors, we can use it as resistors because you can see that the resistance remains almost constant over a wide range of the terminal voltage, which closely resembles the ohmic behavior of a resistor.